Hey everyone, and welcome to today's Explainer. Think of me as your highly caffeinated, enthusiastic study buddy. We're about to embark on a really fascinating journey looking at the fundamental building blocks of our world. We're going to be zooming in specifically on Units 4 and 5 of our chemistry principles today. And the main theme, we're discovering exactly what electrons are up to. Whether they're jumping between atoms to power our cell phones or being shared to build the actual fabric of life, it is all about the electron's journey. So let's get into it.
All right, really quickly, here is our roadmap for today. We've got 5 sections to cover: the power of redox, oxidation numbers, voltaic versus electrolytic cells, an intro to organic chemistry, and we'll wrap up with hydrocarbons and functional groups.
Starting right off with Section 1, the power of redox, transferring electrons.
So, this first half of our journey is entirely about movement. We're talking about electrons actively jumping from one element to another to create energy. Now, to keep this straight, you really only need to remember one absolutely crucial mnemonic anchor, and that is oil-rig. Oxidation is loss of electrons, and reduction is gain of electrons. Seriously, whenever you're staring at a redox reaction and starting to feel overwhelmed, just come back to this. If a substance loses electrons, it's oxidized. If it gains them, it's reduced. It is literally the master key to unlocking any redox reaction you'll see.
And you have to remember that oxidation and reduction are perfect opposites. They always happen together. You just can't have one without the other. The substance undergoing oxidation loses electrons, meaning its oxidation number goes up. We actually call it the reducing agent because it's forcing something else to be reduced. On the flip side, the substance undergoing reduction gains those exact same electrons. Its oxidation number drops, and it acts as the oxidizing agent. A really great mental example from our source material is calcium reacting with solid sulfur to make calcium sulfide. Calcium's oxidation number goes from 0 to +2. It lost electrons, so boom, it's oxidized. Sulfur goes from 0 to -2, so it gained those electrons and is reduced. It's just a perfectly balanced trait.
Moving right along to Section 2, rules for oxidation numbers, keeping score of electrons.
Okay, so we just talked about oxidation numbers going up and down, but how are we actually supposed to track these jumping electrons? Well, we keep score. And honestly, keeping score is pretty easy if you just follow a few core rules. First off, pure elements, like a chunk of solid iron or oxygen gas, they always have an oxidation number of 0. They like to keep things strictly neutral when they're flying solo. For a monatomic ion, the number just equals its charge, like a +1 for a sodium ion. Hydrogen is almost always +1, unless it's hiding out in a metal hydride, where it drops to -1. Oxygen is super reliable at -2. And the big rule? When you add all these numbers up for a neutral compound, the sum has to hit exactly 0, like a perfectly balanced math puzzle.
Section 3. Voltaic versus electrolytic cells, putting electrons to work.
Now that we know how to track these electrons, let's actually make them do something useful. There's a bit of an epic showdown between our two main types of electrochemical cells. First up is the voltaic or galvanic cell. This is basically your everyday battery. It takes chemical energy and spontaneously turns it into electrical energy. It literally just wants to happen on its own. But then you have the electrolytic cell, which is the complete opposite. It takes electrical energy and forces it to become chemical energy. It's non-spontaneous. It is electricity-hungry and needs an outside power source to work, kind of like what we see in electroplating. And here's a huge takeaway to note: the positive and negative signs of the anode and cathode actually flip between the two cells. But, and this is a big but, oxidation always happens at the anode, and reduction always happens at the cathode, no matter what.
All right, let's just take a quick mental breather here. We have completely conquered Unit 4. We saw how transferring electrons bodily from one atom to another gives us things like batteries and electroplating. But that brings up a massive question that pivots us right into our next topic. What happens when atoms decide they don't want to trade, but they actually want to share instead?
And that leads us to Section 4, introducing organic chemistry, the chemistry of life.
Welcome to Unit 5, everybody. This is where carbon steps into the spotlight by absolutely mastering the art of sharing electrons. The secret behind the entire organic world really comes down to one fancy word: tetravalent. Carbon has this incredibly simple but profound ability to make exactly 4 covalent bonds. Not 3, not 5, exactly 4. Because it always craves 4 bonds, carbon can easily link up with itself to build these massive chains, loop into rings, and form crazy complex 3D structures that honestly no other element can manage quite so easily.
And just to ground this chemistry in the real world for a second, consider what these carbon structures actually build. Because carbon forms these specific bonds, it is responsible for almost everything that makes modern life tick, and literally life itself. These carbon bonds store the energy in petroleum to fuel your car. They make up the carbs and proteins in the food you eat. They form our medicines, our plastics, and yes, the very DNA and RNA molecules inside your cells right now. All of it, the whole shebang, comes back to carbon sharing its electrons.
Finally, we hit Section 5, hydrocarbons and functional groups, the building blocks of carbon.
Let's break down the specific families of these carbon molecules. We'll start with hydrocarbons, which, exactly as they sound, contain only carbon and hydrogen. Now, alkanes are completely saturated with single bonds, but watch what happens when carbon decides to share more than one pair of electrons with a neighbor. You throw in a double bond, and suddenly you have an alkene, which is unsaturated. Throw in a triple bond, and it's an alkyne. By tweaking just that one bond, the formula, the 3D shape, and how that molecule interacts with the universe completely changes.
Now, if you want to be able to decode chemical names like an absolute pro, you just have to memorize this prefix list. The prefix literally just tells you how many carbons are hanging out in the chain. Meth is 1, eth is 2, prop is 3, and so on. So when someone says methane, you instantly know, that's a single carbon molecule with single bonds. You know when you see an octane rating at the gas station? Yep, that is referencing an 8-carbon chain right in your gas tank.
But of course, things get more interesting because we don't just have carbon and hydrogen. If you swap out even one hydrogen for a specific group of atoms, which we call a functional group, you totally change the molecule's identity. Slap an OH group on there, it becomes an alcohol, like ethanol. Swap in an NH2, now you've got an amine. And take a look at the amide down at the bottom. That highly specific carbon-oxygen-nitrogen connection is exactly what forms the peptide bonds that link amino acids together to build the proteins in your own body. Pretty wild, right?
So how do all these organic molecules actually interact with each other? Well, they transform through some highly specific reactions. In substitution, parts just swap out. In addition, new atoms basically squeeze themselves into double or triple bonds. Elimination does the exact reverse of that. Combustion is one we definitely all know, that's reacting with oxygen to release a massive amount of energy, plus CO2 and water. And then polymerization is how we take tiny single units, monomers, and snap them end to end to create massive plastics or synthetic fibers.
Which brings us to the end of our explainer today. We started with electrons transferring to power batteries via redox. We ended with electrons sharing to build massive carbon chains. And I want to leave you with this final thought to chew on. How amazing is it that such simple, fundamental rules of electron transfer and carbon bonding are responsible for absolutely everything around us? Literally, from the glowing screen you are staring at right now to the very DNA coiled inside your cells, it all comes down to the journey of the electron. Thank you so much for learning with me today. I really hope this helps solidify Units 4 and 5 for you.